So we're at the very end of section 3 of chapter 8. And actually, before we do this, I wanted to deal with one more situation that I don't know that we completely handled last time, okay? And that is if you have an odd power of tangent or an even power of tangent and an odd power of secant, okay? The good situation is if you have either an even power of secant or an odd power of tangent with secants to give. We actually also dealt with all types of powers of secant and tangent. It got a little bit gnarly when we were dealing with powers of secant. You had to resort to doing things like integration by parts and then solving for the integral that you wanted, and that was a little bit gross, right? But for the most part, powers of tangent were fairly tame, so those could be handled fairly well. But there is one situation that is kind of like the double whammy of, look, neither of the things are going on that I want. That is an odd power of secant and an even power of tangent. So I actually want to do that first here. So let's deal with that. Let me go with the whiteboard view here. And we'll do that first. So what would you do in a situation like the following? What in the world? Okay. What would you do in the situation like the following? Integral of secant to the 5th of x tangent to the 4th of x dx. What would you do? What do you think? Keep in mind, we know how to handle any powers, we know how to handle any kind of lone ranger powers of secant and tangent by themselves. Know what I'm saying? So is there something that we could do here that would help us take advantage of that? Yes, sir, Daniel. Yeah, why not? So what are you suggesting here, Daniel? So secant to the 5th of x, and then you're saying the tangents, if we could somehow turn them all into secants, I think we could take advantage of what we already know about powers of secants, yes? Okay, so what you're saying is to write tangent to the 4th as what, Daniel? Secant squared of x minus 1, and which, by the way, that, my friends, is what tangent squared is, right? Tangent squared of x, yes? But you want that to be squared dx, right? And then if you expand this, okay, so if you expand, then what are you going to end up with? Well, integral of secant to the 5th of x, okay, and then what we have here is secant to the 4th of x minus 2 secant squared of x's plus 1 dx. And of course, if I distribute things, it's going to be the integral of secant to the 9th of x minus 2 secant to the 7th of x plus secant to the 5th of x. And in theory, what should I be able to do? So long as I am diligent and hardworking and willing to suffer a little bit, I should be able to handle any one of those, yes? Those individual powers of secant. I already did secant to the 5th. We actually did that last time, right? And I could work my way up to secant to the 7th fairly easily as well. Yeah? So I just wanted to point that out because at the end of last time, that one example was off the end of my notes and on the next page. So I wanted to return to that, okay? All right, so back to this. Okay, back to this. So what do we do here? What happens if I have an integral of something of the following form? Let's see, might look something like this. You know, maybe it will be something like, you know, the integral of sine of 4x times sine of 3x. And you say to yourself, holy smokes, what do I do now? Now the angles are even different, right? What on earth am I going to do in such a situation like this? Well, there's a couple of formulas that we can take advantage of, and I'm not expecting you to like commit these to memory necessarily, but I do want you to know where they come from. And there are these formulas down here. Sine of mx, sine of nx is equal to that disaster right there. And I at least want to explain somewhat where at least maybe that first one comes from, okay? You guys remember like the sum and difference formula for cosine? Remember anything like that? So like, what is the cosine of a plus b equal to? Does anybody remember? It's like cosine of a, cosine of b, minus sine of a, sine of b. That's what the plus one is, okay? And by the way, these sum and difference formulas for sine and cosine, they do reside within that picture that I drew. Okay? You could actually explain all of these in that picture. Okay? What about the cosine of a minus b? What's the difference going to be there? Well, yep. Okay. So it's going to be cosine of a, cosine of b, plus sine of a, sine of b. Oops, I just accidentally switched to the eraser. Okay. Now, you might be saying to yourself, what does that have to do with these crazy formulas that are sitting down here? You know what I mean? Well, what you can do is you can add these two formulas together. Okay, so like if I added these formulas together, what would happen? What would happen if I add these formulas together? Think about it. I would get cosine of a plus b plus cosine of a minus b is equal to, look, if I add those things together, what happens to the sine business? It cancels out, and you're going to have two cosine of a, cosine of b's. Do you see what I'm saying here? Which is the same thing as slapping a little 1/2 in front of this thing and slapping a parentheses on there and saying that that's equal to cosine of a, cosine of b. You know what I mean? What formula looks kind of like that? Yeah, that kind of looks a lot like this bottom formula right there. Yeah? So I'm telling you flat out that all three of these formulas just come from either adding or subtracting the sum and difference formulas for sine and cosine. Yeah? They look a little bit crazy, but I'm telling you that's where these things come from. Okay? So back up here to this little example that I drew right here, and I don't want to spend a ton of time on this, but what would I say that this is equal to? And the reason these formulas are nice is it allows me to take a product of things and express it as a sum. And that's always nice because then I can break it up as two separate integrals, yeah? Okay, so like sine of 4x, sine of 3x, what am I going to do? Which of the formulas would I use here? The first one. Yeah, the first one. This one right here, yeah? So the 1/2 I could kind of pull out and it would just be the integral of, now think about it, it's the cosine of basically mx minus nx, yeah? And they write that as m minus n times x, all inside of the cosine function, which is a legitimate way of writing it also, yeah? You just factor out the x. So what would that be in this case? So, you know, I think of this as being my mx, and I think of 3x as being the nx, right? So it's going to be 1/2 cosine of what? Just x plus or actually not plus, what is it? Sorry. Minus, okay, minus cosine of, right, you add the two things together, and it's cosine of 7x dx. And then we are seriously in business. Do you know what I'm saying? So this thing is now really easy to deal with. You just have a couple of integrals involving the cosine function that you have to do now. Yeah? That's just something I wanted to point out. You just use these interesting variations of the sum and difference formulas for sine and cosine to deal with situations like that. Okay? Questions? Any questions on that? Yeah, Daniel.
On a test or quiz, would you expect us to
No, I don't expect you to know those formulas, but I just want you to be aware that they exist. Because, so if I were to like ask you flat out, hey, what if you had like a product of two sine functions that had different angles? That you would be able to say, oh, well, there's kind of a variation on the sum and difference formula that helps you deal with that. So I would want you to kind of know what the path forward is and know that those formulas exist. Okay, but I don't care about you memorizing those. Okay? Other questions? Well, okay, need to get out of here. Clear. There we go. Good. All right, so let's move on to bigger and better things. Okay. Section 4. Wait a minute, did I just straight? Here it is right here. Section 4 of chapter 8. Trig substitution. Hey, somebody mind closing that that door back there? Be great. Okay, trig substitution. So far, what have we done? Section 1, I just call that section tricky integrals, okay? Which is essentially what we're doing. We're trying to remember everything that we know and somehow wrangle that into new ways of thinking through integrals. Using completion of the square, multiplying and dividing by the same thing, adding, subtracting the same thing, et cetera, et cetera. That's what section 1 was. Section 2 was integration by parts. Section 3 was dealing with trig integrals, yes? Trig integrals in the sense of products of powers of sine and cosine, or products of powers of secant and tangent. In the first case, sines and cosines, remember, the three identities we tended to use were the Pythagorean identity, sine squared plus cosine squared is 1, and the half angle identities, right? In the case of secant tangent, we didn't even need that level of sophistication. All we needed was the Pythagorean identity, and it seemed like we were able to handle anything, any kind of product of secants and tangents. But we did have to resort to using integration by parts sometimes, right? And that got a little bit nasty, but nonetheless, it's still doable, okay? Trig substitution is gonna feel sort of like I'm doing the wrong thing at first. It's gonna feel like we're making things complicated on purpose. And we are. We are making things complicated on purpose, but it's because we want to turn something that wasn't a perfect square into a perfect square by utilizing trig functions, okay? So that's essentially what's gonna happen. The idea is to use trig functions. Let me just write that in here for us, okay? So the idea is to use trig functions to create perfect squares. And you might say, what? How? Okay, think about it. Tangent squared plus 1 equals what? Secant squared. So on the one side of that Pythagorean identity, you have a sum. That's not a perfect square, right? At least the way that it looks. But actually, it is a perfect square. Tangent squared plus 1 is secant squared, yes? So the idea here is if you have a sum of two squares that doesn't involve trig functions, you kind of put trig functions in there so that then it does turn into a perfect square, okay? Similarly, sine squared plus cosine squared equals 1, yes? And you could write that as cosine squared equals 1 minus sine squared, for instance, yeah? There you have a difference of two things, 1 minus sine squared equaling a perfect square, namely cosine squared. So we're going to use trig functions and the Pythagorean relationships that they have to help us take sums and differences and turn them into perfect squares. That's the whole thrust of what the trig substitution method is all about. And again, it's going to look like we are literally losing our minds at first. It will seem like, good grief, you are crazy. Why would you do that? Look at what you have. It is way more complicated. But believe me, it will pay off in the end because we will have integrals that we did not know how to do that suddenly we will know how to do. Okay? So let's get to it. So you use trig substitution to solve integrals. And a lot of these actually do come up in real world applications quite a bit. To be, some of the integrals that show up involve square roots of things, and that sort of thing happens a lot when you're trying to model situations in the real world. You have square roots of differences of things, and you'll be like, well, how do I deal with that? And then you can use a trig substitution to help you deal with it, okay? So here are the various trig substitution forms, okay? You have the square root of a squared minus u squared, okay? And I want to talk about what to do before we even delve into the weeds with this thing. Does that make sense? So if I have something that looks like the square root of a squared minus u squared, you've already seen something like that before, haven't you? When have you seen it? Yeah, remember the arc sine antiderivative? 1 over the square root of a squared minus u squared du was equal to arc sine of u over a plus a constant. Remember that? Okay. But here I'm just saying this square root basically just shows up, maybe not in the denominator. The square root of this difference of squares shows up in this way. What's the difference, by the way, between the first square root and the, I mean, it's obvious what the difference is between the first and the second, I hope, right? One of them has a minus, one has a plus. But what's the difference between the first one and the last one? Yeah, you're kind of flipping those things have been flipped around, know what I mean? Yeah? So, how do I deal with the first one? How do I deal with the first one? Okay, so here's how we're going to deal with it. Okay? Watch this. Is there a situation you can think of involving trig functions that basically has a number minus the square of a trig function? One minus sine squared? Something like that, right? What would a squared, okay, yeah. So here, let me write this up here. Notice that 1 minus sine squared, I like to use t, all right, is equal to what? Cosine squared of t. So, but I don't have 1 squared, I don't have 1, I have a squared. You know what I'm saying here? So I tweak this formula a little bit by multiplying through by a squared. Does that make sense? So what you do is you say, okay, I'm going to multiply this thing through by a squared. And so this thing becomes a squared minus a squared sine squared t equals a squared cos squared t. You see that? I mean, we're just doing like basic algebra here. You might be saying, okay, what So what? Who cares? Well, what's magic about this is, watch, I'll rewrite this as a squared minus parentheses a sine of t squared equals a squared cos squared t. That might not seem like a super magical, manipulation. All I did was, instead of writing it as a squared sine squared, I just wrote it as a sine all of that squared. Big deal. But now does this not look like, a squared minus like u squared is equal to something, right? Equals a squared cos squared t. What do you think I should put u equal to? What should u be equal to? U should be equal to a sine of t. Yes? And then the a squared minus u squared thing, let me just say a squared minus u squared is going to be equal to a squared cos squared t, which is really nice. Why? Because then the square root goes away. Do you know what I'm saying? The square root of that difference now becomes the square root of a perfect square, which goes away. That's really nice. But what's du going to be equal to? du, what is the derivative of, a is a constant, right? So that just comes along for the ride. A cosine of t dt. Yes? And then what you do is you just follow your nose. So whenever you have something that looks like the square root of a squared minus u squared, you make the trig substitution, u equal to a sine t, and everything turns into a giant trig integral. I promise that's what's going to happen in the end. You're just going to have a bunch of powers of sines and cosines, which, hey, we just did that, didn't we? We know how to deal with powers of sines and cosines. Now, what do you think is going to be the deal with this second guy right here? Let me use a different color, maybe blue. What do you think we're going to do, do with this second guy right here? There you have a number plus something squared. What do you think we're going to do in that case? Yeah, secant squared plus, or a tangent squared plus 1 equals secant squared, right? Another way to say that, I won't go through the whole rigmarole of multiplying through by a squared. I'm just going to write the formula with the a squared in it. So we know that a squared plus a, let me just say tangent t, okay, all of that squared, what's that going to be equal to? A what? A squared secant squared of t. Know what I'm saying? So what does it seem like we should put u equal to in this case? Yeah, we're going to put u equal to a tangent of t. And what is du? Yeah, a secant squared of t dt. And we say to ourselves, all right, what that's going to do is notice that, okay, a squared plus, look, a squared plus u squared is now going to be a squared secant squared of t. Does that make sense? And so a sum of squares turns into a perfect square, which then makes the square root go away again, which is very nice. And we will end up with a trig integral that involves products of powers of secant and tangent in this case, which we know how to do. Make sense? Okay, what about the last one? What do you think we're going to do with the last one? What do you think we're going to do with the last one? Yeah, tangent squared equals basically secant squared minus 1. Yeah. So, so let me write this in green. So a squared, or let me write it this way. Okay. A secant of t squared minus a squared equals what? So basically secant squared minus 1, I've multiplied through by a squared. What's that going to be? Yeah. A squared tangent squared of t. So in other words, I get that u squared minus a squared is going to be a squared tan squared of t. So long as what do I need to put u equal to? A secant of t. And what is du going to be? What's a derivative of secant? No. That's the antiderivative. The derivative of secant. Yeah, secant tangent. Whew, good thing it's not that logarithm thing. Okay. So do you see the rationale for each one of these substitutions? Each one of these is meant to sort of get rid of a square root by turning something that wasn't a perfect square into one. Yeah? And in each case, we'll end up with a trig integral that we learned how to handle in the last section. Okay? Questions? Yes.
What is like the perfect square? All of them. What is the perfect square?
Well, it's right there on the side of the equation that's a perfect square. So like in the first case, a squared minus u squared is now a perfect square. What is it, Daniel? What's the perfect square now? A squared minus u squared is a perfect square now. It's a squared cosine squared. A squared cosine squared is a perfect square because it's squared. Is this a perfect square? Is x squared? Is x squared a perfect square? Why? Same thing here. Thing squared. So it's a perfect square because it's squared. So when you take the square root, that square simply just goes away. Does that make sense? Yeah. I'm not taking the square root yet, but I'm just trying to say, what do I do with the thing under the square root so that it is a perfect square? So when I take the square root, the square goes away. If I take the square root in the second case, it's going to work out nicely, right? Because I have a square root of a perfect square. Does that make sense? Is that clicking, Daniel? I mean, it is a perfect square, right? You're turning that sum into a perfect square. What's the perfect square in the second case that you're turning it into? A squared secant squared of t. Yeah, because a squared plus u squared will be replaced by a squared secant squared. No, you want to get rid of that. Yeah. Okay, so you want to replace it by something that is a perfect square, which the right-hand side obviously is every time. Does that make sense? Okay. All right, yes. Yes, sir.
So what are we doing with this? So we found that derivative of
Well, so the integral is going to go from being an integral in u to an integral in t. And then you're going to do the integral in t instead, but then at the end, you're going to have to go back to the original. So you're changing from the variable u to the variable t. You'll see when we do some examples. But this is all just setup. Does that make sense? I don't want to get ahead of ourselves. We first need to think about what is it that we're trying to do? Well, we have nasty square roots that we want to make go away. And the way that we do that is by turning the thing under the square root into a perfect square. Yeah? We're adding trig when it's not there, which sounds like a bad idea. That's what I was saying. It seems like we're insane. It seems like that we're making something way more complicated than it was before. But the payoff is the square roots go away, and we turn it into an integral that involves trig that we are like experts at handling. Yes? Okay. All right. Are you ready? Okay. Let's do some stuff here. Okay, I'm going to delete this, and I'm going to go, and we're going to do some examples. What in the world's going on here? All right, let's do an example here. Okay, ready? Let's do an easy one. Okay, I don't like writing in red. That's too intimidating. Okay, so here's an example. What about the integral of the square root of 1 minus x squared dx? Let's just talk through this together. What would we do? We're going to do a trig substitution. What's it going to be?
A will be 1 and U will be X.
Uh-huh.
So then U.
So x is going to be equal to something. What's x going to be?
A sine of t.
Right.
1
So
times sine of t.
right. So 1 minus x is going to be equal to, so x is going to be sine of t. Yes. And dx is what?
Dx is
Cosine of t dt. And what's 1 minus x squared? Well, that's 1 minus sine squared, which is, right, 1 minus x squared is equal to 1 minus sine squared, which is cosine squared of t, which is really nice. Okay? So we go over here and we say, all right, all this like, we're sort of complicating effort that we just did is going to turn this thing into something nice. It's going to be the square root of what? Square root of what? Cosine squared of t. And what is dx? Cosine t dt, right? Here's dx. You put that right here. 1 minus x squared is going right there. Okay? Dx is cosine of t dt, which, I mean, the square root of cosine squared. Look, you might say to yourself, is the square root of cosine squared like just straight cosine, or do I have to worry about absolute values, or what? You do have to be careful when you take the square root of a perfect square, okay? But the thing is, we have complete control over the situation, so we just assume that cosine of t is positive. Cosine of t could be negative. Do you know what I'm saying here? Yeah? The cosine function could be negative for various values of t. But you would just choose a range of values where it's not. Whatever, right? Okay, so this is going to be the integral of what? All right, it's going to be cosine of t, which is cosine squared of t dt. Yeah? And how do I deal with that? The half angle identity. Okay, which is 1/2 the integral of, is it plus or minus in the case? Yeah, it's 1 plus cosine of 2t dt. Okay? So now what? 1/2. What's the antiderivative of 1? T. It's very important that you use the right variables because we're going to have to fix this thing after the fact. The original integral was in x. Do you know what I'm saying? The original integral was in x. This answer is going to be in t. So we're going to have to do like a reverse. We're going to have to resub back in and get rid of the t's and turn them into x's. What is the antiderivative of cosine of 2t? Yes. Yeah. Now the fun starts because we need to turn this back into an integral in x. So let me just say, here's a little question. How to turn back, like the integral sign is gone, which is good. Yeah? But we want this to be integral in x. How to turn back into x's. Okay? Well, what do you guys think? Yeah, so that's the thing. Let's go back up here. So let me just, I'll put this in blue so that, we don't complicate things too much. This right here, if x is equal to sine of t, then you know that t is equal to what? Arc sine, you take arc sine of both sides. T is equal to arc sine of x. So that's one thing, yeah? But the other thing is sine of 2t. The problem is, I know what sine of t is. I know what sine of t is. And by the way, I even kind of know what, I even kind of know like what cosine of t is. Because think about this. Remember this guy right here? I had 1 minus x squared is equal to cosine squared, right? So what's cosine of t equal to? Let's just be honest. What's cosine of t equal to? Yeah, that's the square root of 1 minus x squared. So I know what cosine of t and sine t are in terms of x. But what sine 2t? How do I deal with that? How do I deal with sine of 2t? Double angle formula. Yeah? Okay. So double angle formula says that sine of 2, this one's easy. I mean, I actually have this one in my mind all the time. Okay. Sine of 2t is just 2 times sine of t times cosine of t. Okay, I'm kind of writing it up at the top. Okay. So let me just kind of rewrite this thing down here. So this thing is equal to 1/2 t plus 1/2. Sine of 2t is 2 sine of t cosine of t plus a constant. Now that's sort of convenient. The 2's just kind of cancel, right? Yeah? Okay. So what are we left with? So it's going to be 1/2. What's t equal to? Arc sine of x plus. Yeah, sine t is equal to x. Cosine of t is equal to the square root of 1 minus x squared. Plus a constant. And there it is. Now that seems, it seems like, wait a second, how could that have possibly have worked? After all that, like, subbing in, kind of following my nose, converting back to x after moving over to t for a while, how could that have worked? And of course, what can we always do to make sure that everything's above board here? You can take the derivative. So let's try this out. What if I take the derivative of, what was it? It was 1/2 something, right? 1/2 arc sine of x plus x times, now I'm going to write this as a power. It's 1 minus x squared to the 1/2. Okay, what's that equal to? Well, 1/2 comes along for the ride. What's the antiderivative of arcsine of x? 1 over square root of 1 minus x squared, right? That's what the derivative of arcsine of x is, yes? What would I have to do with the second thing? Product rule. So it's going to be the first times the derivative of the second. The derivative of the second is kind of interesting. Yeah, it's going to be 1/2 that thing to the minus 1/2 times negative 2x. Do you know what I'm saying here? Yeah? 1/2, so let me just say it's 1/2 1 minus x squared to the negative 1/2 times negative 2x. Know what I'm saying? That's just a chain rule application. And then I have to go plus the derivative of the first times the second. Well, that's just 1 times what? 1 minus x squared to the 1/2, which is basically just the square root of 1 minus x squared, right? Okay. Now let's see here. Is this going to work? Let's, I don't know. Let's see here. 1/2. It's going to be 1 over the square root of 1 minus x squared. What is this second guy right here? What is that? It's minus, look, the 2's cancel again, right? So this 2 and this 2 cancel, yeah? So it's going to be minus what? X squared over square root of 1 minus x squared. And this is plus the square root of 1 minus x squared. What? This thing doesn't look anything like the original yet. Okay? So we go like this. This is 1/2. Let's see here. This is 1 minus x squared to the first power over, look at, these have the same denominator. Do you know what I'm saying? This is 1 minus x squared over what? What's this? This is 1 minus x squared to which power? The 1/2. And the top thing is to the first power. And here I have a square root of 1 minus x squared. So look at that. If I have 1 minus x squared to the first power over 1 minus x squared to the 1/2 power, what's that overall? What is that overall? Yeah. So this is 1/2. And again, it's just going to be a square root of 1 minus x squared plus another square root of 1 minus x squared, which is 2 of those divided by 2. And what do we get? Square root of minus 1 minus x squared, which is exactly what we had as our original integrand. Does that make sense? Okay. Now, granted, I mean, I will say the following. Granted, these problems at first kind of feel complicated, but they're very mechanical. That is, you just like automatically do a particular substitution and you basically follow your nose. You convert back. You don't have to check it every time. Do you know what I'm saying? The check part was just me being amazed that this thing even worked at all in the first place, you know? But yeah. It looks complicated, but I promise it's something that you'll really get used to eventually. Okay? Yes, Daniel.
When we were taking the integral of cosine squared t, why didn't we just do like a substitution? So like, why didn't we do like substitution cosine t for just u and then u squared? So.
Well, but then, I mean, if you put u equal to cosine of t,
Oh,
there's no sign on the anywhere. I mean, you would kind of be defeating the purpose of doing that. Yes, sir.
So the overall thing is I'm going to make u equal to something else so that something works, and then I'll fix it at the end.
Yeah.
All right.
Well, it's you intentionally complicate it,
And then you fix it.
and then you go back. But I mean, all it does is it turns the integral into a trig integral that you know how to handle, and then you have to reverse course and get rid of the trig functions and put it in terms of the original. I mean, it's very like mechanical. There's not, like once you have it down, you're not really thinking anymore. It's just you just kind of do it. But at first it feels tricky. Yes.
My question is just like, we're using so many formulas. How many of these form like double angle, half angle, like how many of those are you supposed to memorize?
Well, that's 2. So 2. I would memorize the double angle formula and the half angle formula. Those are good formulas to memorize. And of course, the Pythagorean identities are good things to have in mind as well. I actually, I mean, in my mind, I have the sum and difference formulas too, just because they're useful. But the half angle and the double angle identities are very, very helpful. They seem to come up a lot, and they'll keep haunting you. They'll haunt you so much that eventually you'll be forced to memorize it anyways. But yeah, there's not that many. So yeah, I would just memorize the half angle. And the half angle formula, you're really just memorizing one thing. It's basically up to a plus or minus. The double angle is a little bit trickier. The sine one is easy. The cosine one, there's like various ways that you can write it down. We'll see that tomorrow. But we're going to do lots of examples tomorrow of this new tool. Okay? All right. Yeah.
How did like the first person to ever do this just like do it?
I mean, it's a brilliant technique, but eventually they kind of systematized it to where it really doesn't involve much thinking. But the first person to think of it, definitely it was a tricky idea to come up with. All right, that's it.